So in this lecture, we're going to introduce two key theorems. They're going to be really important for addressing a wide array of different functions and their Laplace transforms and inverse Laplace transforms. These are the first and second shifting theorems, and they tell us how applying an exponential in t world turns into a shift in s world, and likewise how applying an exponential in s world turns into a shift plus a cut in t world. Now I'll explain exactly what I mean by all that in this lecture, but for the time being I just want to point out that these two theorems, the first and second shifting theorems, both appear in your table of integrals. I'll point out where they are. So you don't have to remember these theorems, but you do have to know how to use them. Okay, so we're going to start off by looking at the first shifting theorem, and we're going to prove it from first principles. That is, we're going to prove it from the integral definition of the Laplace transform. So let's take a look first of all at that first shifting theorem. So the first shifting theorem basically states that if I have a function that is multiplied by an exponential, e to the minus at, then its Laplace transform will take that function and it will give me a shifted function in S. By that I mean that instead of having a function f of s, which is the Laplace transform of f of t, I'm going to just replace everywhere I see s in this function with the value s plus a. So let's prove this and then demonstrate it. So the proof from the definition of the Laplace transform for any function f of t is going to be the integral from 0 to infinity of e to the minus st times the thing that we're taking the Laplace transform of. Okay, so now we can notice here that I've got an exponential times an exponential, which means I can put those two things together. So we'll have e to the minus s plus a times t of f of t dt. But we notice that this looks exactly like the definition of the Laplace transform, except that s here, e to the minus st, has been replaced by s plus a, e to the minus s plus at. So this is going to be exactly the same as the Laplace transform of f of t, except everywhere I see s, I'm going to replace it with s plus a. So what I mean by f of s here is that this is the Laplace transform of the function without that exponential in front. So you can see that this is a really useful little theorem because it allows me to deal with functions that have little rogue exponentials in front. And this is going to allow me just to turn that exponential into a shift of a function that I can calculate easily from my tables. Likewise, we're going to see that, and this is perhaps even more useful, is that when I have a function in S world that has a shift in it, I can go backwards and find its Laplace transform using this first shifting theorem. So let's take a look at an example of that going forwards, and then we'll take a look at an example of the inverse Laplace transform. So example 1, we have the Laplace transform of e to the minus 8t cosine of 2t. So we know from the first shifting theorem that this will be equals to f of s plus a, where in this case a is equal to 8. We can see that this looks like e to the minus at times a function of t. So our function of t is cosine 2t. So what we need to do is we need to calculate the Laplace transform of this function without the e to the minus 8t in it. Happily, that's one of our table's Laplace transforms. That's going to be s over s squared plus 2 squared. That's the Laplace transform of cosine 2t. And now that I've got big F of s, then it's very easy then for me to just find the Laplace transform of the exponential times cosine 2t by just replacing everywhere I see s, I'm going to replace it with s plus 8. And there we go. That's all there is to the first shifting theorem. If I have a function that is multiplied by an exponential e to the minus at times a function of f of t, then I'm going to calculate first of all what the Laplace transform of that function is, and then I'm just going to shift it by the amount that's in the exponential. So let's take a look at a slightly trickier example, looking at the inverse Laplace transform. So in this case, what I've got to do is notice that this is actually the inverse Laplace transform of a function of s, where everywhere that s appears, it appears in the form s minus 7. That is, this is a shifted function of s. So f s minus 7 is equal to 6 over s minus 7 to the power of 4, which means that the unshifted function, the function with that shift removed, replace everywhere I see s minus 7 with just good old-fashioned s. Now I have my unshifted function, and I'm ready to calculate f of t. F of t will be the inverse Laplace transform of the unshifted function. So it'll be the inverse Laplace transform of 6 over s to the power of 4. Again, we notice that that is one of our tabled Laplace transforms. It's actually the inverse Laplace transform. So we'll get 6 times t cubed over 3 factorial. So that's using the Laplace transform of 1 over, or m factorial over s to the m plus 1. 3 factorial is actually equals to 6, so these are going to cancel beautifully, and I'm left with t cubed. So that's what the inverse Laplace transform of my function big F of s is. Now what's the inverse Laplace transform of the shifted function? So to do that, what I'm going to have to do is multiply now by e to the minus the shift times t. And that's going to be multiplied by f of t. So what I'll get is e to the 7t times t cubed. Okay, so in this example here, we needed to use the first shifting theorem to deal with the fact that we had this shifted version of a function of s, a simple function of s. So we identified what the shift was. It was equal to minus 7. We identified what the unshifted function was, and then we applied the first shifting theorem in reverse. The inverse Laplace transform of a shifted function is e to the minus shift times t times the function. Now let's take a look at a slightly more complicated example. We have an inverse Laplace transform 10s minus 1 over s squared plus 6s plus 3. Now let's take a look at the denominator first. S squared plus 6s plus 3. This is actually something that I can complete the square on. So you may have learned how to complete the squares of a function in high school, and your method might be slightly different from mine, but they all end up with the same answer, so that's all good. So we've got s squared plus 6s plus 13 is equal to some s plus a all squared plus b, so I have to figure out what a and b are. So that will be s squared plus 2as plus a squared plus b. So just by comparing the corresponding terms here, you see that I get 6s is equal to 2a, so that implies that a is equal to 3. And I've got that a squared plus b is equal to 13, which gives me that 9 plus b is equal to 13, which gives me b is equal to 4. So what does that give me? Well, let's take a look at what our function has become. So we've got 10s minus 1 all over this thing here, s squared plus 6s plus 13. So what does that function become once we've completed the squares? We've got 10s minus 1 all over s plus a, so big A was 3, squared, plus b. Now remember, we're using the first shifting theorem here, and the first shifting theorem deals with functions of s where everywhere that s appears, it appears in the form s plus shift. And we can see that that certainly looks like the case in the denominator. I've got an s plus 3, so it looks like my function of s has been shifted by 3. But if I look at the numerator, I don't have a corresponding shift of s in the top. So I need to artificially stick that shift in. And the way I'm going to do that is by taking my function s, adding the shift, and then subtracting it. So you notice I just added 3 and I subtracted 3. Those obviously cancel each other out, so I haven't changed my function in any way. But it does allow me now to rewrite this whole thing as 10 times s plus 3 all over s plus 3 squared plus 4. And I have a minus 3 times 10, so that's minus 30, minus 1, so that'll be minus 31, all over s plus 3 squared plus 4. So let's take a look at what we've got now. We've got a function here where everywhere that s appears, it appears in the form s plus 3, s plus 3. And likewise on this side here, I've got a function where everywhere s appears, and it only appears in the bottom, it appears in the form s plus 3. So I definitely have a function that's been shifted here, and this is called big F of s plus 3. And I can use the first shifting theorem to deal with that. So the first shifting theorem tells me that the inverse Laplace transform of a shifted function will be e to the minus shift times t times f of t, little f of t, where f of t will be the inverse Laplace transform of the function big F with no shift, so the unshifted version of big F. So what is that? Well, just looking again at our expression up here, we had the shifted function big F of s. All I have to do to unshift this function is everywhere I see s plus 3, replace it with s. So big F of s is just going to be 10 times s over s squared plus 4 minus 31 over s squared plus 4. So I just replaced everywhere I saw s plus 3 with s. So that gave me my unshifted function. So now I'm ready to calculate what little f of t is. It'll be the inverse Laplace transform of this thing. And so that's going to be given by my tables as 10 times cosine of 2t minus 31 over 2 sine of 2t. So I'm just using the tables for that. So that's my function f of t. Now what I need to do is put that back into this expression here to find the inverse Laplace transform I'm looking for. So the inverse Laplace transform of big F of s plus 3 will be e to the minus 3t of what I just calculated. So it'll be 10 cosine of 2t minus 31 over 2 sine of 2t. So in this question, we started off with a function that didn't have an obvious factorization here. So what we did was we took the denominator and we completed the squares. And that ended up giving us something that looked like it had a shift in it. So it suggested that we might need to use the first shifting theorem to deal with this shift. The problem was that we only had a shift in the denominator. We didn't have a corresponding shift in the numerator, and the first shifting theorem only applies when we've got a function that has s plus a shift everywhere s appears. So that's easy enough to fix, in fact. All I needed to do was add and subtract the shift on top, so they cancel each other out. I don't change the function. And that allowed me then to rewrite this entire function as something that really is a shifted function of s. Then I'm ready to use the first shifting theorem. Any shift then just becomes an exponential in t world multiplied by my function f of t, which is just the inverse Laplace transform of the unshifted function. So looking again at my function with a shift, everywhere I see that shift, just get rid of it. So I ended up with a function of s, calculated its inverse Laplace transform, and then at the very end multiplied by that e to the minus 3t that comes from the first shifting theorem. Let's take a look at the second shifting theorem. This tells us what happens when I've got an exponential multiplying in s world. What happens in t world is a little bit different now. Here we're going to get a shift again, just like we did in the first shifting theorem, but it's multiplied this time by a heaviside function. So this is going to give me a shift plus a cut. So once again, we're going to prove this from first principles. We're going to prove it from the definition of the Laplace transform. So I'm going to go forward, f of t minus c, u of t minus c. From the definition, this is the integral from 0 to infinity of e to the minus st, f of t minus c, u of t minus c, dt. And you can see that this heaviside function, this step function, is actually going to give me a way of splitting my integral up, because this is going to be 0 between 0 and c, t is equal to c, and it's going to be equals to 1 from c to infinity. So that suggests that I actually split my integral up into two pieces, and I can always do this. Integral from 0 to c, and the integral from c to infinity. So all I'm doing there is I'm splitting up the interval over which I'm integrating into two pieces. Now, why did I do that? Well, it's because the heaviside is actually going to kill off one of these integrals. Because notice here that t is allowed to take values between 0 and c in this integral. My integration variable is t. It can vary between 0 and c. And so this heaviside is always going to have the heaviside of t minus c. It's always going to be the heaviside of a negative number. So this will always be equals to 0. And that's going to kill off my integral here. On the other hand, in my second integral, t is allowed to vary between c and infinity. So t will always be larger than c, which means that this heaviside will always be equals to 1, and the integral becomes quite simple. I'm left with the integral from c to infinity, e to the minus st, f of t minus c. Now, we're not quite there yet. This doesn't yet look like a Laplace transform. It's got too many differences. It's got an integral that goes from c to infinity rather than 0 to infinity, and it's got an f of t minus c here. So what I'm going to do is I'm going to introduce a new variable. I'm going to introduce a variable t prime, defined as t minus c. Now, when I'm introducing a new variable for integration or integration by substitution, I need to find the derivative of that variable. So that will be just 1. And I also need to change the limits. So what is the value of t prime at c at the lower limit, which was c? It's going to be c minus c. It's going to be 0. And what's the value of t prime at t is equal to infinity? Infinity minus c is infinity. So what happens to my integral here? Well, a couple of things. We get the integral from the lower limit becomes 0 to infinity. E to the minus s, well, t became t prime plus c. F of t minus c is just t prime, and dt becomes d prime. So this now looks almost like a Laplace transform, except for this minus s and a c here. So if I could just get rid of those, I'd have a Laplace transform. However, notice that this doesn't involve t. I've got minus s times c. That's a constant for this integral, so I can actually take it out the front. So I've got e to the minus cs times the integral from 0 to infinity e to the minus s t prime f of t prime d t prime. And this is precisely the Laplace transform of f. So this will be equals to e to the minus cs Laplace transform big F of s, where big F of s is the Laplace transform of f with no shift and no cut. So it's the unshifted, uncut function. So what we say here is that the effect of multiplying by an exponential in S world is equivalent to a shift and a cut in T world. So let's take a look at an example of that. Example 4. We have a function sine of t minus pi times u of t minus pi. It's a shift plus a cut. So let's see what this thing is going to actually look like. So this is going to be a function that is, if we write it in terms of a piecewise continuous function, so splitting up my domain into two pieces, t is less than pi and t is greater than or equals to pi. This thing is going to be equals to, for t less than pi, my heavy side will be 0, so this thing will be equal to 0. And for t greater than or equals to pi, this will be a shifted version of sine. So this thing is going to look like a sine function that's been moved over to t is equal to pi. And then it just does its usual up and down. So you notice that there's no discontinuity here because I've shifted and cut this function. Okay, so now let's find the Laplace transform of this thing, and I'm going to use this second shifting theorem to do so. So the Laplace transform of sine of t minus pi u of t minus pi, you see that this is indeed of the form of a shift plus a cut. It's got everywhere t appears, it appears in the form t minus pi, and I have a heavy side also with a t minus pi. So this is going to be equals to e to the minus the shift times s multiplied by big F of s, where big F of s is the unshifted uncut, it's the Laplace transform of the unshifted uncut function. So big F of s is equal to the Laplace transform of the unshifted uncut function. So what I mean by that is remove the cut, so get rid of the heavy side, and remove the shift, so get rid of that minus pi. So that's going to leave me with sine of t. The Laplace transform of sine of t is 1 over s squared plus 1. It's one of our tabled Laplace transforms. So my answer is going to be e to the minus pi s divided by 1 plus s squared. Now let's take a look at a function that is not written in such a nice and easy way. Let's take a look at a function that has a cut in it, but doesn't have a corresponding shift. So in example 5, we've got a function f of t is equal to t squared times u of t minus 3. Once again, we'll use our piecewise continuous definition. So the heavy side is going to change things up at t is equal to 3. So we've got t is less than 3 or t is greater than or equals to 3. So this will be equal to 0 for values of t less than 3, and it'll be equal to t squared for values of t greater than 3. So a sketch of this is simply just a cut version of t squared. So we can almost trace in what t squared would look like. So there it is increasing, but we're not going to turn on t squared until we get to t is equal to 3, at which point this thing is now increasing like that. So there's t squared. For values of t less than 3, we get this thing is equal to 0. And we have to decide what happens at the discontinuity. From our definition here, we see that for t less than 3, it's equal to 0, so this point is not included. And for t equals to 3, it's equal to t squared, so this point is included. And we're also including the point at t is equal to 0. Now, the problem here is that we have a function that has a cut but doesn't have a corresponding shift. So I can't use the second shifting theorem, which requires both a cut and a shift. However, we're going to generate a shift artificially. And we're going to do that using a little trick. We're going to notice that I can write t squared as some function a times t minus 3 squared plus b t minus 3 plus c, where I need to figure out the values of a, b, and c so that both sides are the same. Now you notice that if I can figure that out, then I've got an expression that really is a function that has a shift. Everywhere that t appears in this expression on the right hand side, it's in the form t minus 3. So now I have to figure out what the a, b, and c are that give me the correct expression here. And the way I'm going to do that is by using calculus to do that. Now you could do this just by expanding this thing out and then matching the corresponding expression for t squared and the expression for t and then the constant, and get 3 simultaneous equations for 3 unknowns, and that sounds exhausting. But instead what we're going to do is a much quicker approach. We're going to use calculus and judicious choices of c. Let's start off with my original expression, t squared equals to a t minus 3 squared plus b t minus 3 plus c. And let's look at what this expression becomes when t is equal to 3. So we see that the left-hand side is just going to become 3 squared, it's going to be 9. And the right-hand side, when I put t is equal to 3, that'll die, and I'm just left with c. So that immediately gives me c is equal to 9. Okay, next step. Let's take this expression and take the derivative of it with respect to t on both sides. So I'm taking d dt of both sides of this expression. That's going to give me 2t is equal to, using the chain rule, 2a t minus 3 plus b. Once again, I'm going to set t is equal to 3, and the left-hand side, that's going to give me 2 times 3 is equal to 6. T is equal to 3 kills off this term but leaves behind b, and that tells me what b is. So b is equal to 6. Last step, let's take the second derivative of my function. So I'm taking another derivative. That's going to give me 2 on the left-hand side, and it's going to give me 2 times a on the right-hand side. So that immediately gives me that a is equal to 1. So that's going to give me now an expression for t squared that is in the form of t minus 3. So this, again, is exactly the same expression on both sides. I encourage you to try multiplying this out and showing that, in fact, all that you're left with is t squared. But the advantage of this form here is that it's really expressed as a shifted function of t. So everywhere t appears here, it appears in the form t minus 3. So that my original function, t squared u of t minus 3, is actually now a shifted and cut function, shifted, cut. And the last piece there, even though it doesn't have a shift in it, or because it doesn't have a function of t, so it's actually just a Heaviside function. And I already know how to take the Laplace transform of a Heaviside function. So let's look at the Laplace transform of this piece by piece. So the first piece was t minus 3 squared, u of t minus 3. We saw from the second shifting theorem this will cause a exponential e to the minus shift times s in S world, multiplied by the Laplace transform of the unshifted uncut function. So no cut means get rid of the Heaviside. No shift means get rid of the 3, so that's the Laplace transform of t squared. Laplace transform of t squared is 2 factorial over s to the 2 plus 1. So that's going to give me 2 e to the minus 3s all over s cubed. Next piece, we've got the Laplace transform of 6 t minus 3, u of t minus 3. Again, notice that this is in the form of a shift and cut, so I can use the second shifting theorem to write this as e to the minus shift times s times the Laplace transform of the unshifted uncut function. So get rid of the cut, get rid of the shift, I'm left with 6t, and the Laplace transform of 6t is 6 over s squared. So that gives me 6e to the minus 3s all over s squared. Last piece, Laplace transform of 9 u of t minus 3. I actually don't need to use the second shifting theorem for this because I know what the Laplace transform of the Heaviside is. So that's going to give me 9 e to the minus 3s all over s. So here are my 3 pieces. 1, 2, 3, add them together and I get an expression that looks like this. 9 over s e to the minus 3, 6 over s squared e to the minus 3, and 2 over s cubed e to the minus 3s. Okay, one last example here. We want to find the inverse Laplace transform of a function 12 e to the minus 7s over s to the power of 4. And we're noticing here that this function has an e to the minus 7s in it. So it's in the form of an exponential times a function of s. So let's write down what that is. We get 12 e to the minus 7s all over s to the power of 4 is in the form of e to the minus 7s big F of s, where f big F of s is equal to 12 over s to the power of 4. So, from the second shifting theorem, I know that the inverse Laplace transform of e to the minus 7s, big F of s, will be a shifted and cut version of my function little f of t, where little f of t is the inverse Laplace transform of big F of s. So we saw that that was equal to 12 over s to the power of 4. Inverse Laplace transform of that is going to be 12 times t cubed over 3 factorial. 3 factorial is 6, so that'll give me 2t cubed. Okay, so now I have my unshifted function, f of t, little f of t. I can now substitute this expression in to this over here. So let's see what that looks like. So I'm going to get this is equal to 2 times shift. So everywhere I see t, replace it with t minus 7 and multiply it by the cut. So there's my function using the second shifting theorem. Again, notice that what we had to do here was notice that this was multiplied by an exponential. So we need to, in S world, so that means that we're going to use the second shifting theorem, which means that it's going to turn that exponential into a shift plus a cut in T world. To figure out what the function was, I needed to look at the rest of my function f of s, find its inverse Laplace transform, and then apply the shift and the cut. Let's sketch what this looks like using our usual trick of writing this as a piecewise continuous function. So splitting up my domain into t less than 7 and t greater than 7, I get 0 and 2t minus 7 cubed. So this is going to look like a function 2t cubed that's been shifted to t is equal to 7. Before that value, everything will be equal to 0. And then this thing increases like this. So that's the function 2t minus 7 all cubed. And you see that there's no discontinuity because this is a shift plus a cut. So that's our second shifting theorem applied here to find the inverse Laplace transform.